up and down. And there is some information contained. Because if it would be very fast, at a certain moment you would not be able to resolve. And there is some information. Maybe some of you remember or have it available that is corresponding to some frequency. I'm not sure if you're crazy about this. If you buy an iPhone or whatever, there is a parameter they make advertising with, how many hertz. So this is related to why it has so many hertz, for what reason?
Resolution.
Excuse me?
Resolution. Or
To trick,
yeah.
to make the motion
Smooth
fluid.
it.
Yeah, exactly.
Or resolution.
So I'm not sure what is your handy, your mobile, sorry.
120.
Excuse me?
120.
120, so you are up to date. So that would be definitely an upper limit. We would not expect that frequency to be larger than this. But you remember, it was not always 120, was lower, so probably can go even lower. From movie, the guys who might be interested in movie history, there is a frame rate, if I remember, 25 hertz. That's what you have to have minimum to have these things continuous, fluid. So with the 25 hertz, we could use as an upper limit. So 1 divided by 25 in seconds could be an idea which we use for the upper limit of the time, simulation time. Maybe just keep it in mind. And now just let's do practical work. I should have mentioned before, sorry. I would suggest there are two options. For those of you who have done yourself your static simulation, the one we did before, and you saved it, you can use this one. For all other who now want to do it yourself, in Moodle, at this position, I put a model, a COMSOL model. No sol actually means I deleted the solution that is small. So you could download this from Moodle, and then you have a good starting point for the time simulation. So either way, the third option is just to lay back and watch what I try to do for you. I also have to do the same thing. So let's go in here. Transient. This is the file. I also put to Moodle, the no sol, no solution. The good thing is I also just started now, so if you started now, we are in phase, or you have to wait for me. This is something, with the headline of mechanics, but you also learn how to set up a transient simulation. So if you do your mini project with transient simulation, anyway, you get a lot of information in the according description, but I also show you here as one example. So there's also something useful for that general case. So just to quickly review the model, we defined geometry with signals length. We defined material parameters as Young's modulus and Poisson ratio, the density that was required in the static simulation, and we defined a load position where to attach the mass. Starting from here, I see something is not as intended. There is already a time-dependent solution, so somehow I screwed up with this. I can't fix it. No, I better Maybe I better also download from Moodle, because otherwise I have already settings and maybe it's not consistent if I try to show you. Maybe a good way to check how the download is working. Moodle. So Flatboard, this is the file. I just remember now, in previous semesters in the past, sometimes it was a problem when you download and try to open, but that seems not the case now. Sometimes it somehow changed to a zip or something, but you could immediately open now. That's in a way good news. So I just opened that file which I downloaded. So hopefully this is the correct one, otherwise it's a bit of a problem. While it's starting loading the file in, a transient simulation is usually much more time consuming, takes much longer time, because you can imagine that for every point in time it's doing something like a static simulation, and even more things can go wrong. That's also one of the reasons why you always should start with the simplest one, which is a static simulation. Yeah, now it's okay. I guess you also get that warning that the line graph is not plotted at the moment, which is not a problem because we don't need, but anyway we could. That's because I deleted the results. Maybe that's also interesting to show you, because anyway you would have to do later if submitting your project. Study, now it's cleared. It's not available, but if you want to send your email, for example, your model with the email, for example, then you can clear the solutions, which makes the file much smaller. So that's why he has a problem in showing the data now, but of course you can re-establish the data by just computing it again. So that would be the static simulation we did previous lectures. It goes kind of fast. And then the warning should disappear and we could get it displayed. Yes. So you can reinstall. And now just to be consistent, now you have the clear solution available. If you want to send it by email, you hit this button and then it's getting a small file. So the first study we did was stationary. Now we want to do transient simulation. The first thing you have to know how to get a additional study in here, because the first one came in here with the wizard. So the final thing in the wizard was to choose the study. So how to get another one? It's not, again, by calling for the wizard, by going to the top node. It's here called demoflat root, in brackets root. This is the top node. Make a right mouse, and here you can add studies. So that actually brings us in a menu which you already saw from the wizard. From the wizard. We choose stationary, now we choose time dependent. I think you can double click or add study. So you see we have a second study. We can close this afterwards, just consume. Sorry, it's just consuming space. What we ultimately have to put here is the range of simulated times. I think most of you using MATLAB, so you're probably familiar with this syntax, from 0 to 1 seconds in 100 milliseconds time steps. So you could here change the numbers. You can do it also more convenient if you hit this range button. then you get some more clear support what to do. And you know, from that discussion here, I hope it's reasonable for you that we simulate for minimum frequency of 5 Hertz. So that would transfer into a simulation time, a maximum simulation time of 0.2 seconds. And we put here 1 millisecond step in order to get some resolution. So I put replace. You could also type it in here directly if you're familiar, you don't have to go here. Just to be complete with this, here you have more options. You can make a logarithmic sweep for several decades. So sometimes it's nice to have this menu available. For that simple case, wouldn't be necessary. So this is a adjustment we definitely have to do. Another topic I like to address is when we set up the static simulation. Remember, in the physics section, we put a load, an edge load, here at the end of the beam to see the banding, to induce the stress, the strain, and all the quantities we were afterwards evaluating here. So now, if we do this transient simulation, we don't need that weight on here. So we want to get rid. One option you might do is go to the add load, make a right mouse, don't do it, I just want to show you that it would be possible, and disable. That would be an option, but I would like to motivate you to do a better option, and this better option you find in the study case, step 1 time dependent, where we adjust the output times. If you scroll down, there is something called physics in variable selection. And you can modify things by enabling modify model configurations. So you see something similar to what we did set up in the physics interface. But now if we do changes, it only affects that particular simulation, which is better than you can do your static simulation afterwards, because otherwise you have to remember that you disabled and so on. So the edge load, a right mouse, and here disable. So you clearly see it's not used. But this is, my point of view, a very useful thing. If we would do the simulation now, what I actually would like to see is the frequency of the beam without the load mass. If I would run the simulation, you would see that the result, maybe not so much surprising, is that would look like this, because we need some type of excitement. So there would be different options we could use. A very simple one, and also useful for other reasons, is, we haven't done so far, maybe we should have done it anyway. If this is the beam attached, so we did it better than this, but just for principle, there would be a force deforming it even without putting an explicit load because of the mass of its own. So there is the gravitivity pulls it down, so it already has some deflection. And this is something we might have even used in the static simulation already. I skipped it there for simplicity, but now I will do this. So that means when we start a simulation, it's like switching on at that moment the gravitivity, so that pulls it down, so that gives it some impulse to start moving. So 2 reasons why we do it. First of all, because more realistic, and second, that's something to excite the whole thing. How to do this? We go to solid mechanics. You know, you always find things here, right mouse click. And this is something, usually we do boundary conditions, edge conditions we did last time, and this time we do a volume condition. So in the first section, there is something called volume forces, body load. So we have to select the region which contributes to the body load. So it's obviously the bar or the beam, number 3. And then we go down. The load type force per reference volume is okay. And we like to apply a force in z direction, which pulls in the negative z direction, so it has to be a minus force. And what we need is the constant of gravity, 9.8. COMSOL has tons of constants available. The gravity constant would be already my guess, G. To clarify, it's a constant, you have to put underscore const. That is the way all constants are set up in COMSOL. You could also browse for it. Steuerung space, you can browse for various constants. Times, if you would have chosen absolute mass, then we should calculate, it's not so easy. What mass should we put here? We could not put the mass which would a scale show us if we put this bar on the scale. That's the reason why force per volume here is very suitable, Newton per cubic meter. Some of you have an idea what quantity I have to put here to make it working? I mean, if you ask this is 1 kilo, then you would calculate the force in Newton by 1 kilo times G. But that assumes that you use a center of mass, well, the whole thing. But now we want to have the mass acting in every little space. So we cannot multiply it by one mass. Which mass? So which quantity should be put here to have such a volume force? Some idea? Has to be related somehow to mass, but
The density.
density, perfect, density. And the density, if we look up in the material definition, it makes a mistake because I put the times symbol already. The density is named here root dot rho s. So if we take this quantity here, and use it here, then we should calculate the correct volume force. This is something we should not select or deselect in the simulation case, because it would be also more exact to use in study case 1 for the stationary case. I think that's it. So we now just run the simulation, compute, go to study 2. You have to go to study 2 and compute it. Here is the progress bar and the conversions plot. Maybe already finished. That is kind of very quick. Transient simulation usually takes much longer time. If it takes longer time, it might be interesting for you to go to the conversions plot and know how to interpret this. So it makes several simulation steps in order to simulate the specified time range. And what is typical, it starts with a large number. Actually, that number is the reciprocal of the time step. So if this is a large number, it starts from 0, and the next time it tries to simulate is very close to 0. And then the program has various algorithms to see if things changes fast. For example, if in the beginning it would rise up very quick, it has to do very small time steps. So the time steps are actually not set by the circumstance that we put 1 millisecond, that is just some indicator. It has internal algorithms to check what's the result and then start doing simulations very carefully. If it realizes things don't change very fast anymore, it can do larger steps. So this is basically what you see here. It starts very fine time step and it gets larger, so it can proceed faster. And for some reason, I think that is somehow related to the periodicity of the simulation results. It adjusted accordingly. And if simulation is not finishing, then maybe you find out something here in the conversion plot. It typically would run even higher. It gets more and more larger number, means finer and finer steps, and still not possible to find the solutions. Then you probably have to change something on the model.
Sir,
Yes.
is it backtest? If it makes a big step, would it go back and see if it's changed?
There are various methods. That would be one of the things. So you can even choose which method. The idea here is also it has like a toolbar of various methods, and it tries to find out a very good default setup. And this is what COMSOL is using, but you can adjust it for some reasons. In general, that's not trivial, you know. Of course, because. So now what we got here is a graphic, which is not so useful maybe for displaying. You see here we got a list of times, so we could actually toggle through these times and see that this looks strange, but you have to look for the scale here, 10 to the minus 2. This is actually when the G is switched on. So you see how that thing progresses, but maybe a better way to get more straightforward interpretation of what's going on, that we plot a diagram, as I already suggested before I put the beam in there. Means what type of diagram should we plot? A 1D diagram, that is the way you also should remember if you want to do custom plots. That's certainly something, or maybe something you need for your mini project. So for a diagram like this, y over x or y over t, you go to resolve, choose the 1D plot group, which is just a container to say I want to have a diagram, and then below this you make the right mouse click to see what you can do below. What would be suitable now is the point graph. So you have to click for a suitable point. We could use either of these four, doesn't make too much difference. And then the expression by default is here displacement, which is reasonable. Let's see if we can get the plot now. No plot. We have the displacement magnitude on the y-axis, which is fine. Some idea what went wrong. Some of the typical things you also may occur, you may experience if you do it. What could be the cause that I don't get a diagram? I want to see an oscillating. One indicator is you see there is not time. It says solution number. That might be an indicator. So if you look very closely, there is one point. You see it here. In the solid plot group, the container, there is something called data set. Data set, just below results, there is something called data sets. And here it actually stores the simulation data. Previously, we only had study one. I think we did this cut line here for displaying a certain, I think the displacement along the beam. Now, because we did transient simulation, we got a second data set. So we have to make sure to adjust here the right data set. This is a typical problem which may occur, then you wonder why you don't see any useful result. So we have to change from study 1 to study 2, plot it again, and that looks reasonable. So, what frequency is it? Maybe we take a calculator here and evaluate maybe from here to here. With this type of thing, you should wait a bit until things are established, so not starting evaluating here from the beginning. So maybe from here to here, or maybe I even start here. That is x in that time. In that case means time. Sorry, 0.84. So 0.184. 184. Or 5, whatever. And one period would be here, so minus, this is very easy to remember, 3 times 1, minus 0.111 equals, so that would be the time period, and the inverse of this is something between 13 and 14 hertz. So that would be the natural frequency of that beam, which we found out by this way. Okay, I should save this with a different name. It's anyway in the downloads. Maybe transient. Just to indicate. So in a way, to set up the simulation is kind of simple. For doing it, you basically have to specify the simulation range. The other things were special things, but you always have to set up this thing, so it's kind of easy. Okay, let's go back to the slides. Oh. Did not know, there's another slide set we need later. Here. Where we have been. That was the according EMOLab time-dependent simulation. We just did it. So we talked about stationary time-dependent simulation. Now we move to frequency simulations. And one particular simulation type here is the so-called eigenfrequency simulation. So you actually try to calculate, the program calculates all frequency in which the mechanical structure is oscillating or resonating. I don't start discussing the details of that equation, but anyway, that's the equation solved, and it provides eigenvectors, eigenvalues. I think we just do it. Before doing it, another illustration just from the library. That is some fan, and here you see an animation of one of that frequencies. So this type of simulation is also very easy to set up. Just want to show you again with reference to our flat bar. So again, you may start with the model from Moodle or just continue working on the model you just set up. I think I will just continue working on that one. So what we have to do, first of all, we have to get here a third study, harmonic study. How to do this? Go to the top, make a right mouse, add study, and choose eigenfrequency. Either double click or add study. Close this. So the setup for this is very simple. Basically, you don't have to do anything. Here we can enable the desired number of eigenfrequencies. obviously there are tons of eigenfrequencies, infinite ones, and it calculates the first, second, and so on, and he can decide how many eigenfrequencies you want to see. So if I disable, you calculate 6. Sometimes it can be useful to give here some starting information. I mean, we already know that the frequency we analyzed in the transient domain was 13 Hertz, so we could write here 13 Hertz. It probably also works with 1 Hertz, but sometimes it provides the result faster, and sometimes maybe even a problem, then it's a good idea to give here some starting point. Maybe just try to use the default value to see if it's possible, or if it's able to calculate the things with default values. So the only thing we have to do is just hit compute. So that's very simple. It also calculates kind of fast. Now it by default provided us a result container called ModeShape, and here you got a list of eigenfrequencies, and we can open up, and you see things are consistent. The first smallest frequency it found is 13.5 Hertz, which corresponds pretty much. It was not very precise when I took the measurements of the period of the oscillation. I just did it roughly. I measured between here and here. So at least for me it's convincing enough. That seems to be the smallest eigenfrequency, and we got higher eigenfrequencies. And you can display them, how they look, by just scrolling through them, or even using that buttons here. You see that is the next. It's 84 Hertz, and by using these arrows, we get this frequency, that mode, and we get that mode, so we can toggle through the things. You see, this is a bit more interesting thing. The other one were kind of sinusoidal, that is the torsion mode. So we can toggle through the various modes, or we can also just see at the list what frequencies are available. I have to point out that if you see such pictures here, the amplitude of that oscillation, if you're familiar with eigenfrequency analysis, this is nothing you can take for seriously. It just gives you the mode and the frequency. This is information valid, but how much the displacement is, you cannot get from such a eigenfrequency analysis. Then you would need to do the fourth analysis, which I have on my slides, if you need to know the amplitude. Here you only get the frequencies and how they look like. To get a bit more intuition how these frequencies look like, there's another nice feature, or something you can play around with. You can make movies, animation. Here, player. You can also export this, of course. Here I just do it internally, so you get even a better idea how that oscillation looked like. You can put a repeat forever and start a player. So that is such a mode, and it provides you already with something here in the export node, in the very down. Maybe we make another one. We have to go back to ModeShape. Maybe this one, maybe. And we again make a simulation. So we see how that looks like. Put it forever. If you want to have this movies externally, you would go down to the external nodes and change here target player to file. But then you can choose some, not many formats. you see that one are available, and then you can save it to your file system somewhere, because you can adjust certain properties. For presentation purpose, may be sometimes useful. Okay. So that was this demo, eigenfrequency analysis, and the last one, I don't prepare the demo for it, but I already mentioned if you would be interested in the amplitudes, you would have to run a frequency domain analysis, which would give you the amplitude and phase over frequency, such type of Booty diagram analysis. So that is much more numerically expensive, so it's a much more complicated simulation than this one. So you have to decide what you need. If you only need to have the frequencies, it's a good idea just to use the eigenfrequency analysis. Yeah, not too much details about this. You might already have guessed. How you come with this equation, how this equation comes up, it results from the transient equation when you plug in for the force a harmonic excitation, and the displacement is modeled with also a harmonic displacement. If you plug in here, then you can make the derivatives, first and second derivative, and you end up with this equation. This is the way the equations are derived. Maybe not so important. See you next class. It's a bit early. In the second part, I reserve for a lab, computer lab. I call it computer lab. Maybe we do a break now, like a 10 minutes break, and afterwards we're doing the lab, and it depends how long you take, then we are finished if you finished.
Yeah.
Maybe it's a better idea instead of starting with the lab now, to have a break first. So let's say 3:15. Yeah?
Yeah.
See you. Thank you.